Hello and welcome to the 17th session of the Introductory Biostatistics Distance Learning course. Today we're going to talk about contingency tables, the Chisquare test, and Fisher's exact test. Okay, so if you remember in the last lecture we were talking about inference on proportions. And the way we thought about the data in this one particular example that we were looking at was that we had a dichotomous or binary outcome as well as a dichotomous explanatory variable or covariate. Namely, we were looking at whether people with a certain SNP, which is a single nucleotide polymorphism, it's not really, we're not worried about the science, but whether these people with a certain trait were more likely to have progressive disease. Okay, so we can look at that same data, but in a different fashion in the form of a contingency table. So that looks like this table that I just put up here. Okay, so we just have the same exact data we had before, but now we're just thinking about it in a slightly different way by viewing it as such. Okay, so we have those people who progress as well as the progressors, as well as the non-progressors over here. And then that's the outcome, and then the covariate is whether they have the SNP or they don't have the SNP. Okay, SNP plus means they have the SNP. Okay, so it's the same exact data as before, but now just displayed in this table format, which is what we call a contingency table. Okay, so how can we go about analyzing these data in a slightly different way from the inference on proportions that we did in the last lecture? Well, the way we start when we're doing analyses of contingency tables is that we first assume that the margins are set. What do I mean by that? So the margins are these numbers here. So these numbers here, for example, and as well as these numbers here. Okay, these are like the totals, as well as this number, obviously, as well. Okay, these are the margins. So we assume in contingency table analyses that the margins are set, and then we think about these inner numbers. So the 12, 13, 62, and 103. And we ask the question, if there was no relationship between the two variables, that is to say, if there's no relationship between whether you have the SNP or not, and whether you progress in your disease or not, what would we expect the values in the table to be? So that is these numbers here, A, B, C, and D. Okay? So hopefully you're following along. We're assuming that the margins are set. These are the margins, these numbers here. And we're saying if there's no relationship between the two variables, the outcome and the exposure, here's the outcome is progression or not, the exposure is the SNP, what would we expect the variables in the table to look like? Okay, so let's start with an example with easy numbers to really just bring out this concept. Okay, so I've changed the margins a bit just to make the numbers easy, but the idea is the same. Okay, so we have those with the SNP, those without the SNP, and then whether they progress in their disease or not. Okay? All right. So we've set the margins, that is to say the 100, 100, 50, 100, and 200 are set. So now, if there was no relationship between whether you have the SNP or not and whether you progress or not, then we can calculate the numbers inside that table. So I'm just going to, so for example, this cell here, I'm just going to bring it down here just so I have a little bit more space to work with. If there was no relationship between the SNP and whether you progress or not, then the number that we would expect to see inside this cell here would be 50, which I've gotten from here, times 100, which I got from here, divided by 200, which is the total sample size here. Okay? And it turns out that 50 times 100 divided by 200 is 25. So if there were no relationship between the two variables, whether you have the SNP or not, and whether you progress or not, then we would expect 25 people to be in that first cell. Okay? Similarly, I could do the analogous calculation for this cell, and it would look something like this. I would take 150, which I've gotten from here, times 100, which again I got from here, divided by 200, which is the total sample size, and that turns out to be 75. Okay, so 75. And the calculations for the other two cells would be exactly the same, 25 here and 75 here. Okay, so if there were no relationship, these are the numbers that I would expect to see in my contingency table. Okay, so we can do that same analysis for the actual numbers that we have in our data set. So let me pull those up. I use these numbers just because they were kind of easy numbers to work with in terms of the arithmetic. But now let's look at the actual numbers that we have in our data set. What do those look like? Here are our actual numbers. Okay? And again, you remember in our contingency table analysis, we're assuming that the margins are set. That's why you see these numbers here already. The 25, 165, 190, 74, 116. These are the margins, okay? We're assuming that those are already set, and instead we're focusing our energies on the numbers inside the table. Okay? So we can do a similar, I'm not going to go through the calculation for every cell, but if we were to do it for this cell, what would it be? How would we get the expected? Again, we're calculating the expected numbers in the table. Well, we would take 74, which is here, times 25, which is here, divided by 190, which is the total sample size, and it turns out that that gives us 9.73. So the expected number we have in here is 9.73. And I can carry out that same calculation for all the cells, and it turns out for this one it's 15.3, for this one it's 100.7, and for this one it's 64.3. Okay? So those are the expected numbers if there were no relationship between whether you have the SNP or you don't have the SNP, and whether you progress or you don't progress. That's if there were no relationship. Those are the expected numbers. Okay? So now the question we want to ask is, how different is our observed table from this expected table? This is the expected table. Okay? That is to say, expected when there's no relationship between the exposure and outcome. Okay? All right. Okay, so we're going to test for an association between the outcome and the predictor, and we're going to do so by looking at our observed table and seeing whether it's very different from our expected table. Okay? So we're looking at the difference between observed and expected. So how might we do that? How might we construct our test statistic? Well, you might think, okay, we have 4 cells, and let me have that be the observed. That's the actual number we see in our data set in the table. And then let's call this E, the expected. Okay? And let me just subtract those. Here's the observed minus expected for the first cell, the observed minus the expected for the second, the third, and the fourth. Okay? But you absolutely don't want to do this. Why not? Because the observed minus expected, once you add up the 4 cells, this is necessarily going to add up to 0, right? So if you remember in our very first lecture when we introduced the standard deviation, we took squared differences to calculate the standard deviation, because we had the same problem that we have now. If we just took the differences and added them all up, they'd add up to 0. So that's why we instead look at squared differences, okay? So you don't want to just look at the observed minus expected, but instead you want to look at the squared differences. Okay, so what would that look like? Here's our statistic here. Okay, so remember this big, don't get intimidated by the notation. This big sigma, the Greek letter sigma, just means add, right? And then it says cells down here because we want to add across the cells. Take and then the subscript denotes which cell, so I here. So the observed minus the expected in the first cell squared, right, divided by the expected. And then we add them up all across, right? So if I were to write this equation out, it would be O1 minus E1 squared divided by E1 plus O2 minus E2 squared divided by E2, and so on. And then you just go, here we have 4 cells, so we'd go up to the 4th cell. Okay? So that's what that equation means. Okay? Alright. So it turns out that this statistic, let me just pull up the statistic again on a clean sheet. This statistic follows a chi-square distribution with 1 degree of freedom. Remember before we'd construct test statistics, and then the statisticians somewhere in the background are doing all this hard work to prove to us that it followed a normal distribution or something like that. But this one in particular follows a chi-square distribution. So chi is another one of these Greek letters. And if you want to write it out, it looks something like this. So a chi-square distribution, okay? So what is a chi-square distribution? We're not going to obviously get into the mathematical details. We'll leave those for the statisticians. But just so we have a bit of intuition about what a chi-square test is, if we have a random variable called x, don't confuse these two. This is chi-square. This is just normal x over here, okay? So if we have a normal random variable called x with mean 0 and variance 1. So I write that like this. X has a normal distribution with mean 0 and variance 1. If I then take x squared, then I know that this has a the statisticians have told me that this has a chi-square distribution with 1 degree of freedom. I might add that 1 down here, okay? So that's our intuition about the chi-square distribution. If we take a standard normal random variable and square it, we end up with a chi-square random variable, or rather a random variable with a chi-square distribution. Okay. So what does the picture for a chi-square look like? Let me pull that up. Okay, here it is. So again, you see that it's completely positive, right? You can see that because it's from 0 and so on. It's positive because it's a number that we've taken and squared, right? So if you square something, it can only be positive. And then if we want to capture 5%, remember we use this alpha equals 0.05 all the time. So if we want to have 5% in the tail, the cutoff here, so that's this value here, is 3.84. Okay? That's the magical value for a chi-square distribution in order to cut off 5% the shaded area here. Okay? So, you'll remember, let's get a little bit more intuition for this. You'll remember when we had the normal random variable, right? We said that if we have 1.96 here and negative 1.96 here, that this was 2.5%, and this other side was 2.5%, so that together that it added up to our 5% that we wanted, right? Well, it turns out that if you take 1.96 and square it, you get 3.84, which we just said is our magical value for the chi-square distribution. So hopefully you have a little bit of intuition about what the chi-square distribution is all about. And you'll also remember, so this was our two-sided normal, right? And in our previous picture, we just had the one-sided situation here, and we said 3.84 is here, and it cuts off 5%. So a chi-square distribution is inherently two-sided, right? It's inherently a two-sided test. Okay. So let's do a chi-square test, and a hypothesis test with the chi-square rather, going through our 7 steps of hypothesis testing. Okay. So we write our null. The null hypothesis here is that there's no association between SNP, remember the single nucleotide polymorphism, and disease progression. And then obviously the alternative, I won't write it out, is there is an association. Okay? Then in step 2, we want to talk about the type of data that we have. So here we have a binary outcome, which is did you progress or not, and a binary covariate, which is do you have the SNP or not. Okay? So the type of analysis we're going to do is a chi-square test. And then remember in step 4 and forward, we need our test statistic, our p-value, and so on, which we're going to get from Stata. So let me just proceed as if we've already done the analysis. Our test statistic is a chi-squared value in this particular example equal to 0.99. The corresponding p-value for such a test statistic, it turns out is equal to 0.32. So, and then since 0.32 is greater than 0.05, we fail to reject the null. And then we would say something like, I'm going to run out of space, based on our sample. Remember, we usually want to say based on our sample because maybe if we had a larger sample or just different people, we might get a different outcome. So we say based on our sample, there is no significant association between SNP and progression. Okay, so that is a chi-square test. All right, so let's take a look at what this might, how this looks when we do it in Stata. Let me just pull up the Stata Stata table here. Okay, so remember we already know this formula, or rather this command called tabulate. SNP is our covariate, progression is our outcome. Now we just add this extra piece, which is comma chi-square. Okay, and here we get our chi-square statistic, which is 0.99. Excuse me, and here we get our p-value, which is 0.319. Okay. So it displays the data in this nice format here. Progress no, progress yes, SNP no, SNP yes. And then the corresponding number of people who had each of those combinations. Okay? All right, good. So you might be thinking, hey, you just told us about the test of proportions to do this exact same thing. Now you've taught us a chi-square test. How in the world are we going to decide between these two, since they both apply for situations in which you have a binary outcome and a binary covariate? How am I going to decide between these two? Well, luckily, if you go back and look at the data that we had before, okay, so there were two choices. There was the test of proportions, which we did before, and the chi-square test, which we're doing today. Okay, here was the test statistic. Here it was a z because it was normally distributed. We used the normal approximation. Here it's a chi-square, so slightly different test statistics. But the key point is that the p-values are the same, right? So we get the same result doing these two different types of analyses on the same data. Okay, so hopefully that's reassuring, and it just shows you that these are two different ways to kind of conceptualize the data, but they're doing the exact same thing, and we would arrive at the exact same conclusions, which is in this case that we would fail to reject the null and conclude that there's no significant association between the SNP and progression. Okay? All right. So to give you a little bit more intuition, remember we said that our situation was followed a chi-square distribution with 1 degree of freedom. Okay? So you might be, that's a 1 down here. You might be wondering, why is there 1 degree of freedom? We have 4 numbers in our table, but why are we using a chi-square distribution with 1 degree of freedom? So let's explore that a little bit further. Okay. So again, remember we said that in our contingency table analysis, we take the margins as given, which is why these numbers 25 and 165, 74, 116, and 190 are filled in. The margins we assume are given. Okay? So, but we have these 4 other numbers that can vary, right? A, B, C, and D, for example. Okay? But what's interesting is when you assume that the margins are given or fixed as we do, once we pick one number in the table, the rest of the numbers are known. What do I mean by that? Suppose I put a 3 here. I'm just making this up. You could put any number you want here. But suppose I put a 3. Well, I know that this particular column adds up to 74, right? And if I have a 3 here, then I know that this is going to be 71. Okay? Similarly, for this row over here, this row, I know that it adds up to 25, and if 3 are over in the SNP positive, then I know that they're going to be 22 in the SNP negative. Okay? And then this last one, this D cell, I could get it in any number of ways. I could look down the column and say I know there are 22 out of 116. I could look at the row and say that I know 71 out of 165. Either way, I know that this number is going to be 94. Okay? So that's why we talk about there being 1 degree of freedom. Because as soon as I filled in one number, I put in this 3, all the other numbers dropped out because the margins are fixed. Okay? So that's why we look at a chi-square distribution with 1 degree of freedom. Okay? All right. So we're using this chi-square approximation, and you'll remember, just like in previous instances where we used the normal approximation, it may not always hold, which is why in the past we discussed non-parametric tests. So when should we use this chi-square test? Well, a general rule of thumb is that all cells need to be larger than 5. Okay, so all cells greater than 5. That's a rule of thumb. So large samples. Okay, and that's if we have that situation, which incidentally we may not have here because I put a 3 there, right? So what do we do if we don't have a large sample? Well, if we don't have this, we can do something called Fisher's exact test. Okay. So just a bit of trivia. If someone ever asks you, who's the father of statistics? It's this guy, Fisher. Okay. He was this brilliant guy. I think he was into agriculture, and he was trying to figure out how best to grow his crops. And so he started collecting data and looking at different ways of doing things. And all of a sudden, he became the father of modern statistics. Okay, so the Fisher's exact test is something we can do when we're worried about, these large sample approximations not holding. Okay, so what is Fisher's exact test? So you remember the definition of a p-value. We said that a p-value is the probability of the observed value or something more extreme under the null hypothesis. Okay, and so what Fisher's exact test does is that it looks at a table and determines how many tables are as or more extreme than the observed table under the null hypothesis of no association. Okay, so hopefully this is starting to make some sense to you, because we've seen it a couple times now. We used the same exact concept in order to be able to get a p-value from the Wilcoxon test when we were talking about non-parametric statistics. Okay, and so this is extremely difficult to calculate by hand, but luckily we have computers and Stata to do that for us. Okay, all right. So you'll remember, just to refresh your memory, what did our observed table look like? This was our observed table, right? So let me clear this. Okay. So if I think about tables that are more extreme than our observed table, what would they look like? Well, here's one that's more extreme than our observed table, right? So this would be progression, SNP positive, SNP negative, and so on. Okay, so this is actually our observed table. Sorry, I was getting confused there. This is our observed table. So now if we want to think about things that are more extreme than this, what would they look like? So let me pull up a next table. Okay, so you see what happened here. This is a table that is more extreme. Why is this more extreme? We made 13 in the SNP positive and 61 here, right? So this is a table that is a bit more extreme than the one that we observed. That is to say that the differences are a bit larger. Okay? So we can continue this process of looking at all the possible tables that are more extreme than the one that we have, and see how many there are. We can just count them up. So here I skipped a couple steps, right? Obviously, right? So in the first step, I went from our observed table, and then I just changed one number to make it more extreme. So this is why I added this ... because there are a bunch of other tables in there. And then we can arrive at a table like this. This is obviously more extreme, 24 and 150 and 115, right? So this is a more extreme table. And then finally, if we just kind of keep going, the most extreme table would look like this. So 25, all 25 people who progressed in this table were SNP positive, right? So this is a very extreme example, and if we were to do a chi-square test here, we would note a difference, or a Fisher's exact test. Okay. So basically, all we're trying to get at is when you have a small sample size and you don't want to use the chi-square test because it relies on this approximation, then you can do Fisher's exact test. And the way Fisher's exact test calculates a p-value is it simply counts all the tables that are as or more extreme than the one that we observed out of all the possible contingency tables, and then from there it gives us a p-value. Okay? So we can go through the same 7 steps of our hypothesis testing, but now with Fisher's exact test. Okay? So in step 1, we always write out the null hypothesis, which in this case is that I won't write it out again. I'll just say no association. But if I were to write it out fully, I would say that there's no association between the SNP and progression. Step 2, talk about the type of data we have. We have a binary outcome. And a binary covariate. Okay, the type of test we're doing is Fisher's exact. Step 4, we don't have, there's no test statistic here per se, so I'm just going to say not applicable, NA. But we do have a p-value, and in this case it would be equal to 0.38. Step 6, we would say, well, 0.38 is greater than 0.05, so we fail to reject the null. And in step 7, we would say the same thing that we said before, which is we conclude that there's no significant association between SNP based on our sample again. Based on our sample, there is no significant association between SNP and progression, between having the SNP and having disease progression. Okay? All right, so those are our 7 steps of hypothesis testing. So what would this look like in Stata? Let me pull that up. Okay. So you'll see that the command looks very similar to what we did with the chi-square test. We again write tabulate, we write our covariate, we write our outcome, but now instead of writing comma chi-square, we write exact for Fisher's exact test. Okay? And you'll see the numbers are the same. It displays the data in a very, very nice format. But now it gives us the two-sided Fisher's exact test. This one here is two-sided, which is 0.38. And so since that's a large p-value, we fail to reject the null, and we conclude that based on our sample, there's no significant association between the SNP and progression. Okay. So our results are very similar to what we saw using the test of proportions and the chi-square test. And part of the reason is we have a large sample size here, right? All of these numbers are fairly big, definitely larger than 5. So our chi-square approximation makes sense in this case. So so that should be kind of a relief, right? You know, that means our chi-square approximation for the chi-square test and our normal approximation for the test of proportions, that those approximations are okay. If, however, we had a smaller sample, which is to say that these numbers were smaller, then we would note larger differences between our Fisher's exact test and the corresponding other tests. Okay. So again, remember, we always want to think in terms of what's our outcome variable and what's our explanatory variable or covariate. And so now you can see the progress that we're making. The orange ones indicate tests that we've learned already. We've learned a lot about continuous outcomes. Okay, so remember when we had a continuous outcome with an explanatory, with a dichotomous explanatory variable, we could do a t-test when we thought the normal approximation was okay. If we thought it wasn't okay, we did the non-parametric equivalent, which was the Wilcoxon test. Then if we had a continuous outcome with a categorical explanatory variable, which is to say a variable with more than two groups, remember the t-test was for two groups, which is why we had this dichotomous explanatory variable. Now if we have more than two groups, we did ANOVA, the analysis of variance, and we'll see in future lectures we can do linear regression as well. And then today, and in the last session, we talked about a dichotomous outcome with a dichotomous explanatory variable, and we learned about the Chisquare test. Okay, so you can see we have some more things to learn about, which is the linear regression and correlation for continuous outcomes, and then for dichotomous outcomes we can learn about logistic regression, which you've probably heard about, and then for time to event variables we can do the log rank test, and this is sometimes called survival analysis, and then people sometimes do this thing called the Cox proportional hazards model, or Cox regression, which is something that they sometimes call it. Okay? All right. So let me continue for a little bit. I know it's getting close to the 45 minutes, and I want to be mindful of that. But maybe if we can proceed for just a little bit, then actually, you know what? Let me just stop here, and then we'll have a longer session the next time. Okay, so I'll stop here, and I'll see you in the next session.